Welcome back. Today we'll be doing valid Sudoku. So the question is, we want to determine if a given 9 by 9 Sudoku board is valid. So only the field cells need to be validated. So it doesn't need to be a full filled up Sudoku board. It could be a partial board, but we just want to determine it's valid. So to make sure that it's valid, there's 3 rules in the Sudoku. Each row must contain the digits 1 to 9 without repetition. What that means is, if you look at one row in the Sudoku board, it should only contain the digits 1 to 9 and there cannot be any repetition. So I can have 2 5 in one row. If I have a duplicate, then we know that immediately the entire Sudoku board is invalid. Second, each column must also follow the same rule. So if you look down each column, each of the 9 columns, those also cannot have duplicate numbers in each of the column. And lastly, the tricky part is in each of the 9 3 by 3 subgrids, it must also follow the same non-duplicate rule. So what is the subgrid? So it's this subgrid. So you see this 3 by 3 subgrid, and then this 3 by 3 subgrid. So there's 9 of these subgrids, 1, 2, 3, 4, 5, 6, 7, 8, 9. And in each of these, it can only contain 1 to 9 and also cannot have any duplicate numbers within each subgrid. So the given board, the given input will be a 2D array where each inner array is one row of the board. And if it's a dot, if it's a period, that means it's an empty cell. And if there's a number, then it just represents the number at that index. So to solve this, we need to basically check for 3 rules. So how do we make sure that it is non-duplicate? We can actually maintain 3 hash sets. So we can have a hash set for the rows, a hash set for columns, and a hash set for the subgrids. And each of these hash set will contain the index of the row to the number seen in that specific row. So what I mean is that, let's say we have the row seen hash set, right? So it's a Python dictionary, which is a hash set, and then it will each key be 0, 1, 2, 3, 4, 5, 6, 7, 8. So this 0 to 8 is the row in column index, and the 0 8 to 8 down here is a row index. So we'll keep a set of each of the rows. So this set will contain all the numbers in row 0. Then this set will contain all the numbers in row 1. So let's say if you look at this row index 0, that means as we traverse through the board, we will look at this and we check if the numbers exist in this set. If it exists in this set, we know that definitely it breaks the first rule, and so we can return false. But then if we traverse through everything and all the sets are valid, then that means the row is a valid row. And we can do the same for call scene. So instead of the column index, instead of the row index, it means the column index. So 0, 1, 2, and so on, and it just keeps key. The key is the column index, and the value is the set as we traverse down here. Yeah, and the tricky part of this is actually the subgrid. So we also want to keep a subgrid index. So in sub scene, so this subgrid scene. We can also do the same of 0, 1, 2, 3, 4, and so on until 8. And the reason we can do this is because we can map each subgrid to an index like so: 0, 1, 2, 3, 4, 5, 6, 7, and 8. Right? And then we can keep the set. We can keep the set. So if an index subgrid index 0, it means all the numbers within this subgrid. This is what the set means here. So the tricky part is, how do we map the row and the column to each subgrid? So if you take, for example, column 4 and row 2, how can we correctly map it to the subgrid index 1? So how we do that is basically we have to take the floor division operator. So let's say we have row 2 and column 4, right? With these two numbers, we want to find a way to map it to index 1 so that we can correctly index into the subgrid index, right? So how we do that is we take the row index, we floor divide it by 3, we do the same for column index. So floor division is basically you take 2 divided by 3, and then you find this will be at 0.666, so on, right? And you just round it down to the nearest integer. In this case, it's just 0. So if 2 floor index 3, this will become 0, and column 4 floor divided by 3 will give you 1. So what this 0 and 1 mean is that for the row, it belongs to this subgrid row index. So this 0, and for the column, this 1 means here, because you are the first column of the subgrid. So you can see wherever they intersect, which is this part, will give you the 1, right? So how do we actually find this 1? We have to take the result of this floor division. We do row times 3 plus column. So in this case will be 0 times 3 plus 1, and this will give you 1. So it will, if you take the floor division and then we use this formula, we'll get the correct subgrid index. Then we take this subgrid index, we can then index into the subgrid scene, right? And then if we go through the entire board and all of them does not violate any of the scene, then we can say it's valid. But if at any point we encounter a number that violates the sets, then we just directly return false, because we know the entire board will be false. So let's code out the solution. So let's first get the length of the board, right? So board length, this will be the length of board index 0. So we know board is a 2D array, right? It's an array of arrays. And to get the board length of 9, we index into the first element. So the first element is just this entire array, and we can take the length of it, right? Because in this case we know that it's going to be a 9 by 9, right? But in case we want to make it dynamic down the line, we can just do it here. Next, we have to keep the 3 hash sets, right? So we can do row scene equals to I to set for I in range 9. So this is a Pythonic way of doing this. 0 set, 1 set, 2 set, and then so on and so on until 8. So these two things are the same, right? So this is the row scene, right? Which is exactly what we want here, but this is just a Pythonic way of doing it. Yeah, and then we can do the same for the call scene and the subgrid scene. Alright, now we want to traverse through the array. So we do for row in range board length, and then we do for column in range board length. Okay, then we want to look at the current number, which is just the board index into row and index into column. And we want to check if the current number equals to the dot, then that means it's an empty grid. Then we can just continue because there's nothing here to do. We don't have to check against anything. Okay, so now we do the actual checking, right? So we know the row index is row and the column index is column, so we can just directly check here. So to get the row set for the specific row, we can do index into row scene, index into row. So this basically just takes the hash set and looks at the index in the row and it returns us this set. So then we can do the same for column set equals to call scene and column. So this row and column comes from the iterators up here. Now the tricky part is to get the correct subgrid index for here. So remember how we calculate the subgrid index? We have to use this formula of row times 3 plus column. But this row and column is the result of taking the floor division operator against 3. So we need to actually do row floor divided by 3 times 3 plus call floor divided by 3. And then now we can get the actual subgrid index, which is here, right? This is a subgrid index. We want to get this. We can subgrid set equals to subgrid scene index into subgrid index. Okay, so now we can see that we got the 3 sets, right? Then we can actually check the number against these sets. So if current num in row set, then we want to return false. If current num in call set, we also want to return false. And lastly, if the current number is in the subgrid set, we just return false. And if it gets to this point, that means that this number at that board is valid. And now we want to add that number into all the sets. So we can do row set dot add current number. Call set dot add current number. And lastly, subgrid set add current number. Okay, after all this, if we manage to go through the entire board and none of it violates any rules, we know that the entire board is valid, so we can return true. So let's try running this. Yeah, in row 23, it should be current num. So let me just number current num. Right, save this and let's try running it. So it passes the first test, and if we submit it, we can see that it passes everything and it runs okay. So the time complexity will be O of n squared, where n is the length of the board, because we are just traversing through the entire thing once. So I think that's the best we can do for this time complexity, because you really need to at least traverse through each index once to determine if the board is entirely valid. Yep, so thank you for watching.